Okay, so we have been discussing CPU scheduling algorithms, and we have discussed two algorithms till now. One is the simple first come first serve, another is the shortest job first. And we understood that shortest job first is theoretically optimal. However, this optimality guarantee is theoretical, as in it depends on an estimate of the next CPU burst time. And if that estimate is not accurate, then it won't be optimal. But anyway, so let's proceed. And we have discussed these two methods. By the way, I hope that you have a pen and paper in hand, because today also I'll ask you to work out a couple of examples. Okay, so so the two algorithms we have seen till now, that is first come first serve and shortest job first, both are non-preemptive. Right? That means once a process is allocated to the CPU, it is allowed to execute unless or until it voluntarily gives up control of the CPU. Okay, so these are non-preemptive methods. Let us study one preemptive method also. This is actually a preemptive version of the shortest job first algorithm that we discussed, and it is called the shortest remaining time first. So instead of shortest job first, it's shortest remaining time first. The idea is this: suppose a process is running now. A new process comes in which has a shorter estimated CPU burst time than what is remaining of this process which is running. Okay. So suppose process A is running, it's at this point of time, it still has 5 milliseconds of its CPU burst time left, process A. At this point, a new process B comes in with an estimated CPU burst time of 2 milliseconds. Then immediately the process A will be shifted out of the CPU and B will start running, because the remaining time of A is larger than that of B, right? And this algorithm is shortest remaining time first. Let us see an example. This is the example, right? So see, processes P1, P2, P3, P4 arrive at different times, 0, 1, 2, 3. And they also have CPU burst times different. Right? So how will things proceed? Like, let's say first the CPU burst time is least for P2. So I guess P2 would be scheduled first. But remember that the burst time of P2 is 4 milliseconds. But within sorry, I was mistaken. The arrival time of P1 is 0. So at time t equal to 0, only P1 is there. So it will start to run, right? But then its CPU burst time is quite large, 8 milliseconds. At time t equal to 1, P2 will come in. So what will the system see? At time t equal to 1, 7 milliseconds of P1 is still left, but then P2 has come in with burst time of 4 milliseconds. So in this preemptive scheme, P1 will be shifted out of the CPU and P2 will start running. Okay. So I want you to do this exercise now. Take 5 minutes and do this exercise. Like, if you have understood the scheme, draw the Gantt chart and compute the average waiting time of these processes. If you have any questions, then ask. Otherwise, work out the example. Okay, we have a couple of answers. Maybe let me wait for 1 more minute and then we can continue. So till now everyone seems to agree on 6.5 milliseconds. I'll wait for 1 minute. Okay, let me proceed. So the 6.5 millisecond answer is actually correct. So let me just explain how things are happening. So as I said, at time t equal to 0, there is only P1 in the system. So that will start running. But at time 1 millisecond t equal to 1, P2 comes in. So now the kernel sees that at this point t equal to 1, how much more time, what is the remaining time for P1? It is 7 milliseconds because its CPU burst is 8 and it has executed for 1. However, P2 has come in with a shorter CPU burst, 4 milliseconds. So immediately P2 is scheduled. So this is where preemption occurs. So P1 is, I mean the CPU is, you can say, snatched away from P1 and given to P2. Okay. So P2 executes from 1 to 5. Now remember, at time t equal to 2, P3 comes in. At time t equal to 5, okay, let's say at time t equal to 2, P3 comes in. But then the kernel sees that for the current running process P2, 4 milliseconds are left, whereas P3 has come with a CPU burst of 9 milliseconds. So no preemption happens. P2 is allowed to continue. Right? At time t equal to 5, P2 ends. At this point, what are the systems? What are the processes in the system? P1 is there, P3 is there, but right at this point, P4 comes in. So now the CPU sees, or the kernel sees, that for P1, 7 milliseconds are still left. For P3, 9 milliseconds are left, but P4 has come with 5 milliseconds. Okay, sorry, P4 comes at 3, so P4 comes here. Okay, sorry, I'm sorry for the confusion. P4 comes at 3 milliseconds at t equal to 3. So both P3 and P4 come during this interval. However, P2 is not preempted because at the point when P3 comes in, the remaining time of P2 is less than the CPU burst time of P3. Similarly, at the time when P4 comes in, the remaining time of P2 is shorter than the CPU burst time of P4. So no preemption occurs. At time t equal to 5, P2 finishes, then the kernel sees that what are the processes in the system, P1, P3, P4. P4 has the shortest remaining time first. So P4 is scheduled. P4 runs, then P1, because remember P1 has already executed for 1 millisecond. So the remaining time is 7 milliseconds. Whereas for P3 it's 9. Therefore P1 gets priority. P1 is assigned first. After P1 ends, then P3 is assigned. So this is the average waiting time. Any questions? Okay, so we have discussed the shortest job first, which is non-preemptive, and shortest remaining time first, which is a preemptive version of the same thing. So both of these, they depend on some estimate of the next CPU burst time, which is like in practice quite difficult to estimate. Let's move on to some other kinds of scheduling. Next, what we will discuss is priority scheduling. So from the name itself, it should be clear that here processes will have priorities. By the way, have we already discussed priority scheduling? Have we already discussed priority scheduling? Or this is something completely new? Exactly. So Soumitra, good answer. What we have not discussed priority scheduling per se. However, if you understand the shortest job first, which we discussed, you can think of it as a special case of priority scheduling, because there the processes are ordered in inverse order of their CPU burst time. So you might think that shortest job first also assigns priority to a process, but the priority of a process is inversely proportional to its CPU burst time. Okay. So that way we have not discussed priority scheduling in its name. However, it should not be completely new. So let's see. Yeah, so in priority scheduling, a priority is assigned to each process and CPU is allotted to that process which has highest priority. This also can be preemptive or non-preemptive. And as we discussed, SJF is a special type of priority scheduling where priority is the inverse of the predicted next CPU burst time. Okay. So priority scheduling, I hope you understand how it can be preemptive or non-preemptive. The question is, suppose a particular process is running. Now, a higher priority process comes into the system. So will the currently running process be immediately shifted out and the higher priority process run? Or will the currently running process be allowed to complete? That makes this difference can make the scheme preemptive or non-preemptive. Okay, so here is another example. Again, for simplicity, we have assumed that all the processes come at the same time t equal to 0. However, now the difference is that every process comes with a priority. Okay, and so this number, the lesser the number, the higher the priority. Okay, the lesser the number, the higher the priority. So what would be the average waiting time? Remember, lesser the number here, higher the priority. So P2 has the highest priority, then P5 and so on. So can you just work out this example? Yes, good. Many of you have got it. So it's 8.2 milliseconds. And this is quite simple. I'm not showing the Gantt chart, but many of you have got it, right? So here we assume non-preemptive, but again, I leave it to you as a task to figure out what can be the difference if we consider the preemptive version of priority scheduling. So if a higher priority process comes, then the current process would be immediately stopped. That I leave as a home task. Okay, So now here also the question is how to assign the priority of a process. Who decides it? Now understand that there are two broad approaches. One approach is assigning a static priority value to a process. This is what we saw in the example. So a process will have the same static value throughout, a process will have the same static priority value throughout its lifetime. The other process can be, or the other mechanism can be that the priority of a process varies. Okay. So the simplest case is that a particular process is assigned a priority which remains the same throughout its lifetime. But then there is a issue, that is, it can lead to starvation or indefinite blocking. So suppose there is a low priority process, but it never gets the chance to execute because continuously higher priority processes come into the system. Okay, so that's a known drawback of such static priority assignment. So then what can be done? Can you give some ideas? So the simplest static assignment of priority seems to have this problem. It can lead to starvation of low priority processes. That means low priority processes never get the CPU. So what can be some approaches? That means some dynamic approaches, as in maybe we will, let's say we allow the priority of processes to change over time. So then what would you suggest? See, this is a small example of trying to be fair, right? So, okay, a process has low priority, but that does not mean that we should never assign it the CPU. So what can be done? Okay, yes, I can see some good answers. So like Shomitra says aging, Pankaj says exponentially increasing priority with respect to time. Yeah, Akshat also has the same thing, Shubham says. So you have got the correct idea that possibly priority needs to have priority needs to be some function of time, right? So let's see. So you are right. So let's see. So there is a concept called response ratio. And what is the response ratio is this. So two factors are taken into consideration. What is the CPU burst time and what is the time since arrival? Okay. So we will still follow that principle, as in if a process has CPU burst time low, we will try to schedule it first. Because we know that, as I remember again, that SJF has this nice property of being optimal if you can estimate the CPU burst times correctly. So you would not like to sacrifice that part completely. We still want to consider CPU burst time while scheduling processes. But the new factor which comes in is this time since arrival. Right? So for a waiting process, if the time since arrival increases, then this Rn value increases. This is what you also are pointing out, some of you, that if a process is having to wait for a long time, we should be considerate towards it. We should increase its priority. Otherwise, a low priority process will never get the CPU. Right. So if the time since arrival increases, we should increase its priority. So this response ratio will increase if time since arrival increases. And as Shomitra pointed out, this process is also called aging. So as the process ages more, as the age means this time since arrival. So as the process is aging more, we are increasing its priority. Right? Like again, this thing comes. This idea. I've been telling you this right from the start of the semester that often people in systems, people use ideas similar to what we do in real life. So I guess you understand that like there are certain advantages given to senior citizens in the society. So it's kind of like that. That if a process has been waiting for long, give it some more priority, give it some extra advantage so that it can compete with the higher priority processes. Also, if the CPU burst time is low, then also this response ratio will increase. Right? So basically here the scheduling algorithm will favor processors with having a low CPU burst time and If a process is being made to wait for a long time, then its priority will increase. Okay. Now, let me just tell you a particular mechanism in Linux, the Linux OS, which actually implements this. So, in Linux, a particular process has a value called a nice value. Nice value ranges from -20 to 19. -20 is highest priority and 19 is lowest priority. And default nice value is 0. Okay. So every process in Linux is accompanied by this nice value. And this is often taken into account while scheduling. Now, of course, then does this give a mechanism of giving our process highest priority? Unfortunately, no. So, okay, there are these two commands, nice and renice, used for setting and changing the nice value of a process. But unfortunately, a user can only decrease priority of her processes. Okay? That is why the command is called nice. The idea is you can be nice to others by decreasing priority of your process. By default it is 0, but if you think that you want to be nice to others, then you can set the nice value of your process to higher than 0, which means lower priority. However, you cannot arbitrarily increase priority of your process. That can only be done by the super user or the root user. Only the super user can increase priority of a process. Okay. A normal user can only decrease your priority. That is why the command is called nice. I mean, it gives you the option of being nice to others by decreasing your own priority. Okay. Any questions here? Otherwise, we move to the next algorithm. Any questions? Okay, let me proceed. Oh, what is super user? Super user is the root user. So every system has a root. So if you have worked in a Linux system, you will know that every Linux system, at least Linux or Unix system, has a root user or a super user who has lot more power than a normal user. So if you think of the departmental servers, etc., then some lab staff or some faculty member would possibly be the super user. Of course, if you have a Linux machine on your home, then possibly you are the super user. But the super user has a lot of extra powers which normal user does not have. Like a super user can create new users, it can delete any file, etc. Whereas as a normal user, your power will be limited to your home directory. You cannot go to some other user's home directory and delete a file unless that user has given you permission. But a super user can do all these things. The super user can create new users. It can go to anyone's home directory and delete files, etc. Of course, super user is a trusted person. It is not assumed that super user will start doing malicious things. Any other question? Okay, let me. Okay, Ram Nivas is asking when the slide said user can decrease nice value. It did not say the user can decrease nice value. It said user can decrease priority of a process. Decrease priority is by increasing nice value. So nice value, like negative is high priority and positive is low priority. Okay. Okay, let's proceed to round robin scheduling. Okay, Srihash, another question. How often would the response ratio be calculated? I would guess every time. Okay, wait. First of all, Rashil is asking, while calculating response ratio, why are we adding 1? We are not adding 1. Where is adding 1 coming in? So Rashil, can you unmute yourself? I'm not getting your question.
Sir, we are effectively doing time since arrival divided by CPU burst time plus 1.
Okay, yes. Okay, fine. So yeah, time since arrival divided by CPU burst time plus 1. Yeah, I mean, this, okay. Okay, why are we adding 1? This may be that we want to avoid the value 0. That can be a simple answer. So basically, when the process has just come in, then time since arrival is 0. So it's fine if we want to go ahead with a value of 0, but it seems that in this scheme, values start from 1. That is why it is at least. I mean, just the process should start with a value of 1. That's the only reason I can think of. Okay. So another question from Srihash is, how often would the response ratio be calculated? And I think Pankaj is asking the same thing, computing the Rn value every millisecond. And recomputing priority for every process might be taxing. Yes, it may be. So again, see, the time since arrival, I guess, is the kernel notes that. Right. So time since arrival, it is noted by the kernel. Simply because I don't know if you know, but in Linux, Unix, etc., you can actually ask for the CPU time that a process ran. There are commands for that. So definitely the kernel keeps a track of how much time or how much CPU time the process has used or when the process has come in. These things definitely are kept, I mean the kernel keeps a note of these things. So whether this takes a lot of time, this I really doubt how much extra time this would take. The kernel is, anyway, the kernel notes down how much time a process has, when a process has come, how much CPU time it has got. All these things the kernel anyway notes down because you can actually ask for such statistics for your process. You can figure out how, but there are commands in Linux which you can ask that how much time your process took or how much CPU time your process took, etc. Therefore, the kernel is noting down these things. Now, how much time this kind of a addition and division will take, or yeah, like time since arrival divided by CPU burst time, I really don't think this will take so much time that it will significantly increase the overhead of scheduling. And to answer Shriyash's question, how often would the response ratio be calculated? That's a good question. I would imagine that every time the scheduler is actually invoked, maybe it will do this small timekeeping for every process in the ready queue. Okay. So every time the scheduler is invoked, it will do this calculation for the ready queue for all the processes in the ready queue and then decide which process to run next. I don't think this will take too much time. Okay, and Soumitra has a question. Does aging happen for processes while running? Of course, that's the idea that The more time a process runs, it's okay. No, again, I'm not sure of the question. What do you mean? Does aging happen for processes while running? Again, Soumitra, I'm not sure of the question. Can you unmute yourself and clarify?
Sir, time since arrival means from when the process is coming in the latest time in ready queue, or from when it was first come in the ready queue.
Yeah, when the process was first brought into the system.
Okay. So, sir, when it is going on in the CPU, so the time since arrival is also increasing. So it's means so Rn value is increasing. So this is also aging, doesn't it?
Sorry, I did not get the question again.
Sir, time since arrival is the includes the running
time since increases, but what's your problem? As in, what's your question?
Sir, so sir, this is also a type of aging, right? Because this is running in CPU, so only for waiting process it is not.
No, of course, for every process, time since arrival is kept a note of.
Okay,
but
sir.
most of the processes will possibly get the CPU and complete. But maybe there are a couple of processes which were not given the CPU for a long time, and therefore they are waiting for a long time. For them, this matters and the RN increases. But in general, this process, this mechanism is carried out for all processes.
Okay, sir.
Okay. Okay, so let us go ahead with the next algorithm, which is round robin scheduling, which is more like what happens actually in modern OS, etc. So the round robin scheduling is defined for time sharing systems. A small unit of time, which is often called the time quantum or time slice, is defined. Typically, it's say 10 to 100 milliseconds. The ready queue, now the ready queue here is maintained as a circular queue. The CPU goes around each process in the ready queue and executes it for one time slice. And the timer is set to interrupt the CPU at the end of each time slice. Okay, so this is more like what we have been discussing. There is a particular time slice or time quantum, and there is a ready queue, which is maintained as a circular queue. Fine. The CPU goes around each process in the ready queue and executes it for one time slice. Right. So, what do you think? This mechanism is preemptive or non-preemptive? Yeah, by definition, round robin scheduling is preemptive, because if a process has executed for one time slice, it will be forced out of the CPU and the CPU will be allotted to the next process. Right? So by definition, this is preemptive, and this is how it is managed, that a timer is set to interrupt the CPU at the end of each time slice. We have discussed this mechanism in a bit more detail earlier. Okay, so now the thing to understand is that once a process gets the CPU, two things can happen. First is the process has a CPU burst of less than one time slice. Maybe it executes for a small amount of time and then asks for IO, or asks to wait for a child to complete. So the CPU burst time is less than one time slice, and therefore the process releases CPU voluntarily within its time slice. The second situation is that the CPU burst is more than one time slice. So the process actually wanted to run longer. However, at the end of the time slice, the timer will interrupt. Therefore, a context switch will happen. This process will be put at the tail of the ready queue, and next process is loaded from the ready queue. So we have discussed these mechanisms just to close the loop. So this is what round robin scheduling does. One of these two situations happen. Either a process voluntarily gives up the CPU within its time slice, or it executes for its time slice and then the timer interrupts and then context which happens. So again, here is one example which you can work out. If the time, so suppose this is the three processes. For simplicity, we assume all of them arrive at time 0, and these are the CPU bursts. Now the time quantum is 4 milliseconds. Okay, the time quantum is 4 milliseconds. Then what is the average waiting time? We take a couple of minutes and work this out. Assume the schedule P1, P2, P3. Okay, I see a few answers, 17 by 3, let's see. So yeah, you are right. So this is how the Gantt chart will look like. So P1 will start running, but it will run for 4 milliseconds. After that, P2 will run. Now see here, P2 has a CPU burst time of 3 milliseconds. So here again, see, the P1 was preempted. P1 wanted to run longer, but after 4 milliseconds, it was preempted. However, P2 did not want to run for the whole time slice. It just ran for 3 milliseconds and then it voluntarily gave up the CPU. Then P3 also, same thing. It ran for 3 milliseconds and it voluntarily gave up the CPU. So in this example, you see both preemption and non-preemptive giving up of the CPU. So it's simple. I see many of you have got it. So let me move ahead. Now a bit of analysis of this round robin scheduling. So suppose there are n processes in the ready queue and the time slice is delta. So now you can say that each process gets 1 by n CPU time on average, okay, in chunks, but this 1 by n CPU time may not be obtained together. It may be obtained in chunks, and each chunk lasts for delta time or less. Okay. So if you think maximum waiting time for each process is what? It's this. n-1 multiplied by delta plus sigma, where sigma is the scheduling overhead. So between two runs of a process, so a process was given one slice, at some later point of time it was given another slice. How much can be the maximum waiting time between these two? Is this n-1 plus n-1 multiplied by time slice delta plus sigma, where sigma is the scheduling overhead. Now let me claim this, that suppose delta is very large, then typically, I mean, this round robin scheduling reduces to FCFS. Why? If delta is very large, this slide claims that round robin scheduling kind of reduces to FCFS. Why is that? Yeah, I mean what Shreyas has answered, since the time slice is very large, possibly most processes anyway finish by then, right? So suppose you are working with a large delta or the large time slice, most processes will have a CPU burst less than that delta. Therefore, there is no preemption, etc. And basically, the scheme becomes similar to FCFS. Yeah, so basically what Soumitra said, every process once given the CPU will be completed within delta because delta is so large. On the other hand, if delta is very small, then there is a large number of context switch, which is again not desirable because context switch is overhead. Like the state of one process has to be saved, state of another process has to be loaded, etc. So these are all overhead. So we do not want to have too much of context switch. So therefore you see there are both disadvantages of very large delta and very small delta. So delta is somewhere like, I mean, it's designed, I mean, it's chosen through years and years of experience, but it is somewhere, I guess, between 10 and 100 milliseconds. Of course, there is another requirement here. We want sigma to be really small, even much smaller than delta. Right? So typically, so delta would be say 10 milliseconds, but sigma would be 10 microseconds. And because again, sigma is scheduling overhead, and we want the overhead to be very low. And that is why we have been saying that we want the scheduler to be very fast. There is no point in designing a very complicated scheduler which takes say delta by 2, because then there will be too much overhead in the system. Okay. Okay, here is an exercise for you to work out at home, that for these processes, compute the average turnaround time for different values of delta. Average turnaround time and average wait time. Okay, this is an exercise which you can do at home once you get the slides. This is just to understand how varying delta can affect things like waiting time, turnaround time, etc. Okay, let me move on to the next scheduling algorithm, multi-level queue scheduling. Okay. So even before going to there, let me just ask you, what do you think could be the idea, basic idea of this process? Multi-level queue scheduling. Like queue scheduling we understand, like we have been talking about a ready queue, etc. But why is this multi-level? What do you think is the intuition here? Yes, Shubham has the like a close answer. Multiple priorities. Yeah, Akshat also. So that's the idea. So let's see. So the ready queue is partitioned into multiple queues or separate queues. So for example, this is an example. I'm not saying this is exactly done. So some processes will be interactive, or they will be running in the foreground. The user will give inputs, etc., etc. Some other processes will run in the background. These are called batch processes. So they do not need to interact with the user. Maybe they will simply read a big file, do a lot of operations, and then write to another file. So there is no interaction with the user. So the system can decide to give different priorities to these two different types of processes. Okay. So the interactive processes will be given in the foreground queue, and the batch processes will be stored in the background queue. And typically, each queue will have its own scheduling algorithm with some higher priority possibly to the foreground queue. Here's another example. Let's say here in this picture, again, I'm not saying this is what is done, but this is a picture to demonstrate the idea. Let's say the ready queue is divided into 4 different queues: system processes, interactive processes, interactive editing processes, and batch processes. And the different queues have different priorities. System processes have highest priority, then interactive processes, etc. And each queue may have its own scheduling algorithm, right? So maybe I mean, again, these are just, I'm telling from my imagination. Maybe that system processes are executed in a round robin way, but interactive processes are scheduled in shortest job first idea or something like that. But yeah, these are just like, I'm talking from my imagination. I'm not claiming that these things actually happen, etc. But the mechanism is there that you can think of ready queue being partitioned into different queues, and then different queues being scheduled slightly differently. Right? So now one thing to understand is that scheduling should be done between the queues also. So suppose you say that, let's say we go for this kind of a scheme that the processes in the foreground queue will all be given higher priority than the processes in the background queue. In that case, there will be possibility of starvation. That means maybe there are so many processes in the foreground queue that a process in the background queue is denied the CPU for a long amount of time. That may not be always desirable. So another possibly better idea is this, that again think of that round robin scheduling what we discussed, time slice. So the better idea may be each queue gets a certain amount of CPU time which it can schedule among its processes. For example, 80% of CPU time is given to the foreground queue and 20% is given to the background queue. And maybe it may be that the foreground queue is using round robin scheduling, but the background queue is using FCFS. But it is guaranteed that 80% of the CPU time will be given to the foreground queue and 20% would be given to the background queue. So again, all these mechanisms are there. I'm not saying this is exactly what is used in the OS, but I hope you get the idea that this can also be a practical way of doing things, that you have multiple queues, some with queue processes of higher priority, some with processes of lower priority, and then you divide the time into the different queues according to some principle. Okay, so I see the question by Soumitra, but I guess this answers it. If not, then you can ask again. Okay. Fine. But okay, but let me ask some of you that, so we have discussed the simplest scheme like fixed priority scheduling, like serve all processes from one queue and then go to the other queue. We understand that it can lead to starvation. So we discussed one possible, solution, that divide the CPU time between the different queues. Of course, the higher priority queue should be given more CPU time, but also give some time to the lower priority queue. However, apart from this, there is another mechanism of preventing starvation. That is by changing one point which is written in this slide. Can you point that out? Let me repeat my question. We want to prevent starvation. One way is this: divide the time slice, divide CPU time in some ratio between the different queues. But there is one other mechanism of preventing starvation by changing something in this slide. What is written in this slide? Can you point that out? Yes, I see that some of you have guessed it, like Pankaj, Ishan, Somnath. So this point here, that a process is permanently assigned to a particular queue. What if we change this? What if we have a scheme like a process will start at a low priority queue, but again that concept of aging, that if the process is not getting CPU time for a long amount of time, then shift it to a higher priority queue. So the question is, do we allow processes to move from one queue to another? In this scheme, multi-level queue scheduling, that is not allowed. A process is permanently assigned to a particular queue. But there is another scheduling algorithm which is called multi-level feedback queue scheduling. Here, processes will be allowed to go from one queue to another. Okay. So yes, we allow processes to move between queues. So here also, say IO bound and interactive processes will be in high priority queue. However, a process waiting too long in the lower priority queue will be moved to a higher priority queue. This is another mechanism of avoiding starvation. Okay. So just to say, I mean, again, this is an illustrative picture. I'm not claiming this exactly happens in OS. But let's say we have three queues. The first queue does round robin scheduling with time quantum 8 milliseconds. The second queue here, this one, Q1, that also does round robin scheduling with time quantum 16 milliseconds. And the final queue, the FCFS, this does FCFS. I mean, sorry, this does FCFS. Okay. So, what do you think is the idea of this kind of this scheme? What do you think is the basic idea of this scheme? Yes, of course, priority increases further down the queue. So Q0 has this processes in this has highest priority. Processes in Q1 have slightly lesser priority. Processes in Q2 have even lower priority, and so on. That's what is written. A process in Q1 can execute only when Q0 is empty. However, why do you think the time quantums are different, etc.? What is the idea there? Why do you think is? Yeah, okay, whatever you are telling is correct, but I am specifically asking, why do you think the time quantums vary? Or does that have any relationship with the priority? Okay, Pankaj, see, what you are telling, that is exactly not happening. You are telling a process of higher priority gets to be executed for longer times. But that is not the case. The reverse is the case. The highest priority queue has a low time quantum of 8 milliseconds. And the lower priority queue has a higher time quantum of 16 milliseconds. So what you are telling, the reverse is actually happening. And that is what I am asking. Why do you think this is the case? Yeah, so Ramnivash is kind of going towards the correct answer. Let me just tell you in the interest of time. So the idea is this. Okay, let's just first say okay, now stop your answers because we are already over time. Let me just tell you what the idea is. So first of all, the idea is that this Q0 has higher priority. So processes in Q0 have higher priority than processes in Q1, and processes in Q1 have higher priority than processes in Q2. So a process in Q1 can execute only when Q0 is empty. Similarly, a process in Q2 can execute only when Q1 is empty, etc. Also, a process in Q0 can preempt a process in Q1 or Q2. All these mechanisms are there. However, this is the idea that I was which I was asking for specifically. Why is the time quantums different? So if the CPU burst of a process exceeds delta, then it is moved to a lower priority queue. Again, the idea is similar to what we were studying in SJF and all. Processes which can complete with a small amount of CPU time are given higher priority. So the idea is this. Say a new process enters Q0, and when it gains the CPU, it gets 8 milliseconds of CPU time. If it completes within that, good. If it does not finish in 8 milliseconds, then its priority is decreased because it is moved to the Q1. There, when it next gets the CPU, it will be now given 16 milliseconds. So we are giving it a higher time quantum and we are giving it a higher chance of completing. If it still does not complete, then it is moved to Q2. So this is kind of penalizing a process for taking too much CPU time. Right. So if a process is taking too much CPU time, you reduce its priority. That's the idea. So basically, long running processes may starve here because, as I said, they are being reduced. I mean, they are being moved from higher priority queues to lower priority queues. Right. So this permanent demotion of priority may hurt processes that change their behavior. Example, say it's unlikely, but then maybe a process has lots of computation at the beginning, but later it shifts to interactive mode. Suppose you write this kind of a program which does a lot of computation in the beginning, but then it shifts to interactive mode. But then those programs will suffer because since it has a lot of computation at the beginning, its priority will be decreased. So by the time it reaches the interactive part, maybe it is having a very low priority. Right. So yeah, these kind of problems are there, and therefore some solutions have also been proposed. That one is a periodic priority boost. So all processes are moved to high priority queue periodically. Then again they will be left off. I mean, if they take too much CPU time, they will be brought down into the queue. But this is kind of a periodic priority boost. So all processes are moved to high priority queue. Also, there can be another idea which is familiar to us, priority boost with aging. That is, recompute the priority based on the scheduling history of a process. If you see that a process is in the, say, low priority queue for a long amount of time, you can consider aging and then give it a priority boost selectively. Okay. So again, this is usually done for all processes, and this is done for a particular processes which have been waiting for a long time, etc. Okay, so we have discussed these 6 algorithms. Now, most possibly none of these are really used in an OS. An OS may quite use a hybrid scheme, like the last one which we talked about, like multi-level feedback queue. This is actually a hybrid scheme. Different queues can use different algorithms like FCFS, SJF. There can be concept of aging. There can be a periodic priority boost. So basically, the last algo that we discussed is actually a hybrid of many other of the algorithms that we discussed earlier. Okay. Fine. So sorry for overshooting the time for a few minutes, but I just wanted to complete this topic today. So fine. Let's end this class now. If you have any questions on scheduling, you can ask me next week. Thank you.